Welcome, students. So, where we last left off, we were talking about acids and bases and their interactions. In this video, we are going to now attempt to quantify that acidity using the pH scale. So let's go ahead and get started. The pH scale is a scale we use to help give context to these wide ranges in concentrations. That a strong acid or a dangerous acid can be the concentrations of 1 molar, or could be even fractions of 1 molar, and still be rather dangerous. So while changes in concentrations are harder for our brains to grasp, but a nice little logarithmic scale is a lot easier. Logarithmic in this case means base 10. This is one of the few times we'll use a log and not a natural log. But because these are small numbers instead of really large numbers, we will use a negative logarithmic scale, which just means we'll take a negative log of base 10 to the concentration of hydrogen, essentially protons, or hydronium. And what this will do, it'll turn it into a positive number that we can easily measure. Now, since Kw is 1 times 10 to the negative 14, means in most situations our pH with water as a solvent is going to range from 0 to 14. 0 to 14. With neutral water being right smack dab in the middle, where negative log of 10 to the negative 7th would be a pH of 7. And so with that in mind, whenever we say something is acidic, because it's a negative logarithm, we're going to get a number that is lower than 7. 6 is just barely mildly acidic. 5 is getting a little bit more acidic. When we get down to 4 or 3, it's pretty acidic. If we get down to 2, 1, or 0, it is very acidic and it's very dangerous. Above 7 would be basic. 8 or 9, maybe mildly basic. We can start to get to 10, 11, it's getting significantly basic, with getting close to 14 being very basic. Now the P, there's discussion of where that actually comes from, but the pH, the P and the H could be considered a power. It's a power function of hydrogen concentration. So we have a lot of P functions where we take the negative log of some value or another. So pH is the first one we'll use. Now, when calculating this, there's a question about significant digits. Like, where should I round? Where should I round? And this also comes because this is a power function of a scientific notation number. The number before the decimal of our pH scale is due solely to the scientific power. So like 10 to the negative first is going to give you a pH between 0 and 1. 10 to the negative second will give you a pH between 1 and 2. And so the first number, or any of the numbers before the decimal point, are not actually significant figures when it comes to calculating pH. The numbers presented as the factor that goes before this, the power, those will be our significant digits, and those will be reflected by where we round after the decimal. So if I have a concentration of 0.075 molar, which is the same as 7.5 times 10 to the negative second, when I take the negative log of this, I'm going to get a number that's 1.12 something something something. Now I should round it to 1.12 because I have 7.5. if I did a pH of 2.38 times 10 to the negative 11th, these three numbers are our significant figures. And so when we do the negative log, we'd get a pH that is in the basic scale. The 10 to the negative 11th says it's between 10 and 11. And then 238 converts it into 10.623. So we can do the negative log. It's very easy to do on the calculator. We can calculate this, but where you round it is up to, you have to think about this a little bit. But usually, most cases, to 2 decimal points or 3 decimal points are usually good enough in most situations. Now, there is another factor we need to consider, and that is pOH. pOH has the relationship to the OH concentration in the same way that pH has the relationship to the H plus concentration. So pH looks at the acidity, pOH looks at the basicity. In terms of high pH is basic, low pH is acidic. Well, high pOH is acidic and low pOH is basic. That they are directly related. And so that just how Kw relates H plus and OH minus, similarly we can relate pH and pOH. That we have that relationship Kw equals H plus times OH minus. If we take the negative log of both sides, we get that 14 equals pH plus pOH. So if we know the pH, we know the pOH. They must always add up to 14 at 25 degrees. So a pH of 3 would be a pOH of 11. A pH of 6 would be a pOH of 8. They must always add up to 14. Now please note, we need to always check whether the problem we are answering asks for pH or pOH. And we must always check whether we are given an acid or a base. Because if we take the pH, if we take the negative log of an acid, you get pH. If you take the negative log of a base, we get pOH. So we need to factor that in and do a quick conversion if we need to, if there is. So, some real quick problems. We have 0.3 molar HCl. We have 4.0 times 10 to the negative 4th molar HI. And we have 5.2 times 10 to the negative 2nd molar NaOH. So let's solve them in quick succession. Okay, so negative log of H plus is going to give us pH. So with that in mind, I just need to take the negative log of 0.30. And that's going to give me my pH of my acid, HCl. So I take the negative log of 0.30. Now, you'll notice it gives me a whole string of numbers. The number that, the 0, is because it's 10 to the negative 1st. It's between 0 and 1. And the two numbers I need to record are the 5 and 2. pH of 0.52. So very, very acidic. I record 2 decimals because of 2 decimals. HI is also a strong acid, so I just need to take the negative log of 4.0 times 10 to the negative 4th. There's many different ways to type this in, but we'll just do the simplest one. Negative log of 4.0 times 10 power negative 4. The negative 4 says it's going to be between 3 and 4. So we get 3. Since it's 4.0, that's going to control where those two numbers went at. So this one rounds to 3.40 pH. 3.40 pH. Now, this one is a base. So the negative log of an OH minus is going to give me a POH. Easiest thing I can do is just take the negative log of that. So negative log of 5.2 times 10 to the negative second is what? Negative log 5.2 times 10 to the negative second. The negative 2 puts us between 1 and 2. The 5.2 tells me I round at 0.28 POH. However, I want pH. Well, 14 equals pH plus POH. So 14 equals pH plus 1.28. Solving for pH, well, 14 minus 1.28 is simply, so pH is 12.72. Done. There is another way to go about doing this. It is the same, but I personally think it's a little bit more difficult. H plus, OH minus. So I'm going to find my H plus concentration first. That's the other option. So 10 to the negative 14th equals H plus 5.2 times 10 to the negative second. So I have to divide 10 to the negative 14th by 5.2 times 10 to the negative second. So H plus equals 10 root negative 14 divided by 5.2 divided by 10 root negative second. And I get a H concentration was 1.92 times 10 to the negative 13. Technically, I should just round it to 1.9. So these are my two sig figs. And take the negative log of 1.9 times 10 to the negative 13th. Negative log of 1.9 times 10 negative 13, and that gives me, what do you know? It gives me 12.72 again. So two different ways gives you the same value. Two different ways gives you the same value. Personally, I found my way to be a little bit easier, but both ways gets the same number. 0.52, 3.40, and 12.72. Now, what about going backwards? If I have pH and I need to figure out what is my concentration of H plus, if pH is equal to negative log of H plus, what is the reverse relationship? So, one thing to note, a logarithmic relationship says log is equal to base of x of the log of the y is equal to the answer z. Well, if I take that base and I raise it to the power of z, that will give me the answer that is y. So a log base 10 of y, which is what we've been doing, would equal z. So 10 to the power of z will give us y. So essentially, the inverse of a log base 10 is root of power 10. So if I say take 10 to log 10, they cancel out. Now, however, since this is a negative log, the concentration of H plus is 10 raised to the power of negative pH. So whatever our pH is, we take the negative and raise it to the power of 10. What 10 to the power of whatever that is, and that will give us our concentration of H. So, a couple more problems. I'm asking, what is the pOH of 0.7 molar HCl? pOH. If I have 12.30 pH LiOH, what is the H plus? And then also, what is the OH minus of that same situation? So let's go back to the doc cam and see what we can see. So, with that in mind, the easiest thing to do first is find the pH. So the negative log of 0.7, since I only have 0.7 and I know other sig figs, negative log of 0.7. And so what is my pH? Negative log of 0.7 is 0.2. I have to round to 0.2. Well, pOH is going to be 14 minus pH. So 14 minus 0.2 is going to be 13.8. 13.8. Now, I'm actually going to solve. So, this one first. So, I've given a pH of LiOH. So, pH of 12.3, and I want to convert that into H plus. So, 10 to the negative 12.30 is going to be equal to H plus. So to do this on my calculator, I'm going to 10 negative 12.30, and that's going to give me 5.0 times 10 to the negative 13. Negative 13 has to do with the 12. That is going to be between 12 and 13. And the 30 is going to give us the fact it's 5.0. Now, that is the H plus. To get the OH minus from that same situation, since we already have this, 10 to the negative 14 divided by our H plus is going to be equal to our OH minus. So we have to take 10 root 10 to the negative 14. And I'm going to divide it by my answer right here. If I do that, I get, what is my concentration of OH minus? My concentration of OH minus is going to round to 2.0 times 10 to the negative second. Because this is so dilute, this is so very concentrated. And that is how we would go about doing that. So, as I said, watch what was being asked for. If you do that, it should come relatively easily. Now, this is the last slide we'll go over on this video. But we have a way of measuring the pH. We have a way of essentially quantifying acidity, but how do we go about measuring this pH? And that's where we come into this slide. There's two key ways we typically use. The one way, which is a potentiometric detection, and the other one is a colorimetric indication. Now, potentiometric detection, it uses a pH meter. That it has a it measures a voltage that creates by a differential between proton concentration. That protons naturally, in all ions, will create a small amount of charge, and by measuring this charge difference based on the protons, we can get a very accurate reading. Now, this is slow, but if you've calibrated this correctly, this can be relatively accurate. We usually want 2 to 3 standards for the most accuracy. So we're going to essentially make these solutions, prep them, and when we do that, it's going to tell this concentration is going to have this voltage, and that's going to have this pH, and then we can compare those relative charges to our sample. Now, there's also pHs that can cause color changes. The idea is that there are certain molecules that are pH active, meaning that in base it strips a key acidic proton, or in acid it adds a key acidic proton, and they cause a difference in light absorption such that we see a color change. And these ranges where this color change occurs are well known. And so by using these ranges, we can tell when something has gone acidic, or something has gone basic, or something has gone very acidic or very basic based on these color changes. The idea that we can say when this has gone below pH 2, this has changed from red to yellow, or yellow to red. Or there's various pH paper that is essentially soaked certain chemicals that change color depending on the acidity or basicity. There are certain papers that will change various colors that we can compare against a color chart to say what is our pH range. Or there's other guys that just change one color, like will change red in acid or blue in base. And that we can tell whether it's generically acidic or basic. But the idea, colorimetric indicators have clear color changes, like phenolphthalein is clear in acid but pink in base, and it changes around like pH like 8. There's some guys that go yellow to blue or even red to yellow, and so they have a variety of different color changes based on the indicator and based on the pH range. And that has to do with the light absorption properties. Those are generically useful, but it also, they're fast. They're not as accurate, but they are very fast and very easy to see. But that's where we'll stop for today. And on the next video, we'll start to look at weak acids and introduce our K expressions back into here, because not all of our situations involve strong acids.